Everything seems to be working. Okay, we're in business, it looks like. I'm going to download today's lecture. And we'll do today's lab in a second. I think Ella, I'm almost positive Ella does the CDAG that I was talking about before too. So I'll stay here to work. I think Corey might have gone to CDAG as well. Is Corey down there? For y'all?
No.
Yeah, I'm pretty sure Corey's gone too. So, we can try to answer questions through the IDN for your lab as well. Okay. So this is chapter 13 in the book. This is the 12th meeting period. So I put week 12 or module 12, but we skipped a chapter in the book.
Dr. Avery, can you share your screen with us down here? Or do we need to do that?
I did press share down here. Is there a iTech person across the hall?
I think so. I'm going to
Share is what I have to press. Do you have both of your screens on? Whoa! Because now I have a picture of you.
stop doing that. I think you'll get hot.
Now we don't see our thing anymore. Oh, here we go. Do you have anything yet? Well, what you might want to do is just follow along with the slides.
Yeah, we have
The PowerPoint. I can make a sound, like in the old, remember the 90s and the 80s when you watch the slide projectors. Maybe that you all remember that. We had in school we had assemblies where they get everybody together. Watch a presentation, but there's no moving video. I mean, there were, obviously, but in these things, I have a conversation, and there would be a beep, and then you press. Anyway, old technology. All right, I'm moving to the next one. So the first slide, just an introduction. I'm on to the second slide here. Models in GIS. So. We actually have a course on spatial modeling. That's a course that I'm teaching this semester as well, but this is kind of like the second level GIS course. So we've learned, during the course of this course, we've learned about the basics that you need to know about GIS, raster and vector data models. We've gone through and we talked about projections and coordinate systems. And once you have a grasp of all those things, we started talking about analysis. And then finally, what that is leading to is this concept of spatial modeling. And it's trying to take a process, whether that's a decision-making process or trying to model an actual real-world process, like we've done a little bit of this, the flow of water off the surface of the earth. And that's where we're going with this. So models can be dynamic or static. That means that they can change over time, or they can just be similar, just be the same. And we do cover a lot of these in the GIS course, a dynamic spatial model. For example, we could model the growth of a invasive species. That's something that we do as a lab in the other course, where the invasive species responds to changes in the environment. So the spatial data sets that represent things like precipitation or temperature over time that the invasive species would respond to. We can model where it would be in certain time periods, and that way we can make a dynamic spatial model. Today we're going to do, the model that we're going to do in the lab would be considered a static spatial model, where we're just not considering time, we're just looking for ruffed grouse habitat. It's a little bird. We're looking for the habitat that this bird would like. So we're going to test for, we have certain type of trees that this bird likes, certain types of land cover, and so on. So we're going to try to find that using a static spatial model, or a model of one moment in time. So what we're really going to look at for today's lecture, we're going to talk about this concept of cartographic modeling. I introduced this concept a little bit the last time we met. We talked about analysis. It's really the chaining together of spatial functions in order to answer a question. That's really what cartographic modeling is all about. So there's that same concept in the sentence. Application of spatial operations such as buffers, interpolation, which we didn't cover in this course, but we do cover in that advanced course. Reclassification we covered, and overlay to solve spatial problems. Well, it just says to solve problems, but to solve spatial problems. So doing something like a suitability analysis, often they're static, for today. You can include a temporal component, changes through time, like the example I just gave, or a different one. So dynamic spatial models are dynamic in both space and time. So for every time step in the process, the data has to change. That's what makes them spatial. You can model the growth of a city over time. You can model the spread of a wildfire. Anything that has both a spatial component and that changes over time. In the case of a wildfire, you could have a GIS data layer that represented the fuel. You have a GIS data layer that represented the wind direction. And then your model could, at every time step, could determine based on functions like proximity, how much nearby area is on fire, how much downwind nearby area is on fire. You see how you could ask those questions depending on the data type. You might buffer all the existing things that are on fire, or buffer them in a certain direction, downwind. How much fuel is there, and that could inform a decision on whether or not that next area caught on fire. So those are the types of things that we talk about in the next course. And those are some examples of spatial temporal GIS models. So that last lab that I'm talking about, not today's lab, but well, it's kind of like today's lab. Today's lab is actually pretty short. It's only a couple pages of things to do. But the final lab is even shorter in terms of the text. It's only a page long, and it's not very descriptive on what you need to do. And so it's important as you do today's lab that you really understand the question that you're trying to answer every step of the way. Because the process of cartographic modeling is to take the data sets, the spatial data sets, determine which spatial data sets you need, and then get them to answer the questions that you need answered by chaining them together. So the reason that it's called cartographic modeling is that each step involves taking GIS data, running a tool or an operation on that GIS data, and then getting a different GIS data set as a result. So if that was a buffer, you're buffering points, you're asking where are the areas that are within a certain distance of this area. You run a buffer and you get an answer. These are the areas that are within a certain distance of that buffer. Then you might do an overlay, because the real question you're trying to answer is how many people live within a certain distance of these things. So you might do an overlay. What kind of questions can you answer with cartographic modeling? There are a bunch. So today the lab is this kind, the distribution of suitable habitats or viable populations. That can be animals, but it could also represent humans. It could represent grocery stores. Trying to find where things should go based on the surroundings are questions that you can answer with cartographic modeling. You can look at migration routes, corridor studies, water distribution systems. Talked about we brought that up a little bit in this course. Species invasions, where are we going to put things, whether it's a mill site or a new grocery store, pollution response planning. These are all things that you could do with cartographic modeling. So here is an example of a cartographic model. And oftentimes it's helpful if you want to figure something out, and you're pretty sure that a GIS can do it. It's helpful to create a flow diagram like this to get you to the answer. Right? So here in this case, this is a lot like the lab. We're trying to find a suitable area for, let's just say, for the rough grouse, like the lab's trying to do. Okay, so suitable area for where's this this bird likely to live. If we can determine that its habitat is driven by being close to lakes, but not close to roads, and that it likes wetlands, this is a little different than the lab setting, but maybe this is a different animal. But, what we can do is take the lakes data and buffer it, and we find out the areas close to lakes. Take the roads, and remember we said not close to roads. So it takes the roads buffer. In the roads data, we buffer it, and we come up with a roads buffer. So it likes to live by lakes, but it doesn't like to live by roads. So we can do a overlay operation. We might have to find out specifically what type of overlay operation. But there's one that's called erase. We talked about different overlay operations a couple weeks ago. One called erase, and that would give us this output. These are the areas that are close to lakes but not close to roads. It never fails to just do a union. Remember a union overlay? If we union these two layers, and then select out which areas were close to the roads. That would also work. It's another type of overlay that would work here. That's why that just says overlay as a general circle. So we're removing those areas that are close to roads to find out the areas that are just close to lakes but not close to roads. So that's what this slide here is. Okay. But we also are looking for certain types of wetlands that are close to lakes. So we do another overlay that determines. Oh, actually, that's it. Well, let's go back to here for a second. We're looking for certain types of wetlands. Okay, certain types of wetlands. So in order to get certain type of wetlands from this hydric status layer, we need to do a reclass. We've done that in labs before, right? gone to a particular column and said, okay, well, I only want, we did it with soils, I think, in another lab. I only want these types of areas. So we're reclassing the hydric status to wetlands. These are the wetlands where this particular animal likes to live. And then we do a intersect overlay to get only those areas that are within the wetlands and within the buffer. So we intersect those two. Intersect gives us the areas that are in both the wetlands layer and the combined buffer. And then finally, we do a reclass to determine those areas that are suitable. And this example is actually fairly basic. It just gives us those areas that are suitable versus those areas that are not suitable. It may be that we employ a little bit of math in there and come up with areas that are somewhat suitable, very suitable, I should go the other direction. Very suitable, somewhat suitable, not suitable, and definitely not suitable, or something like that. In that case, we could assign certain weights to these layers and put those as attributes in an attribute table. So cartographic models are often represented with flowcharts graphically like this. There's just another. This is the same flowchart, another representation of this same flowchart. So here it is with pictures. But if you were just doing this in your head, you might draw a flow diagram like this. And lots of times I like to get a little bit more specific with my circles when I draw the flow diagram. Think about exactly what type of overlay you want to do. And sometimes I'll say what I'm reclassifying, the column I'm reclassifying. So if it says reclass, I might actually write reclass the wetlands column. And intersect overlay versus up here would be an erase overlay up here. Erase overlay, intersect overlay. Now, this class, we mostly have focused on raster data, but vector data, but we did spend a couple weeks talking about raster GIS data. And so it's important to know that you can do cartographic modeling with raster data. In fact, some ways it's easier to think about because it's numbers. I like thinking about that. So if we had two raster GIS layers, and we decided that in order to get a suitability layer value, we would take criteria, the layer A, and multiply it by 2, layer B, and multiply it by 4, and that would give us our overall suitability layer. I didn't think about doing this beforehand, but I just thought of doing this. Let's see if it's even open, even turned on right now. But this is a website that we developed a couple years ago that does this like dynamically. I mean, it's doing GIS on a computer, but it's showing it to you on the web. So when what happens is that there's for this oyster habitat map, there's a raster GIS layer that's driving this depth score, the salinity score, in other words, the average salinity for the area, the existing oyster reef score. All of these are different GIS layers. And as I move these little slider bars, all I'm doing is changing the weight. So I'm multiplying salinity score by a higher number. And so the reason that this website was created was to allow decision makers to come in here and say, okay, well, if I want to focus on certain oysters, oyster habitat to restore, to set aside, what of these things is more important to me? So I can move the slider bars around and see which oysters are, what's the score? Are they high value or they're low value? They're low, medium, and high, maybe output, just by moving them. So question?
Yeah, so with that North Carolina, are they actually using your thing to try and conserve, or are they not caring at all and just keep going?
Yeah, I mean, that's always the question, right? Are they actually using it? I haven't, like I said, we made this a couple years ago, and I was the GIS person, so I don't know policy-wise. That is a great question.
Okay, that's because I recently did have the coast as a marine biology student.
Oh, cool.
I heard tell that the oyster council down there doesn't even listen to the marine biology club that this is on.
Right. Yeah. I mean, one of the big issues that I see in all sorts of, because I was in the Caribbean for a week, and we were actually doing, we're flying drones, and also we built this boat drone that goes and takes a bunch of pictures of the reef, and so we're collecting data on the coral reef there, and it's inside of a protected area, which it's supposed to not have people taking, but there was people fishing there almost all the time. So, yeah, you gotta have, you gotta have enforcement and all sorts of things. But yeah, I mean, it's a good. Basically, I'm saying it's a good question, but I have no idea if they're actually following that. But the reason for bringing this up was more to show the functionality here, and this could be done with. Maybe a socioeconomic thing would be looking at crime. So you have different crime layers. You could show a map. Let's say each one of these represented a different crime layer. And you could pull up, petty thefts and weight them higher than robberies or something, and you can see the hotspots change because you'd be multiplying those different values. You could just have it be demographics, and you could weight certain demographic groups, people with kids, higher than other groups if you were looking to sell things to people or something like that. It doesn't have to be oysters in this case, or oyster habitat. All right, so this type of overlay is often called weighted linear overlay. You have a linear function, you're multiplying things by different weights. And I mean, obviously the question is, what do these weights mean? Do they really mean anything? In some cases, they actually are real numbers. You could, if this was a layer like temperature and elevation, and you were trying to kind of predict the growing season right there. You might have precipitation, temperature, and elevation, and you could use those three layers to predict those kind of values. Sometimes it's just a policy decision. You're just trying to weight something to come up with a number to provide a gradient over the landscape. All right, so It can be done in raster or vector. Also, in both raster and vector, these suitability rankings can be both discrete, meaning that you just get either a 1 or a 0, or maybe a 1, 2, 3, 4, 5 answer. Things fall into different categories, or a continuous rank layer where you get a number that may even have a decimal place associated with it, and you get a continuous rank layer. You have to think about what your needs are. The real trick is the questions that are kind of being asked here is, what's the basis for the rankings? Do the rankings really mean anything? Sometimes they serve their purpose if they're just simply rankings. This area is better than that area for the particular thing that we're looking for. But it's best to have kind of like a scientific relationship or mathematical relationship you've established between something like health risks and a predictor for health risks. Here we've got mercury concentration. Lots of times, particularly in conservation applications, which I work a lot in, there are things like, they're negative externalities. They're negative things that affect the habitat that you're looking at. So things like the distance to roads can negatively affect different things more than other things. Different habitats are more fragile than other habitats. So you can make a road suitability layer by taking the roads layer and calculating the distance to the roads. And sometimes you have to think in your head, okay, well, what I actually want, the relationship is the further you are from the road, the better, right? And so at first you create a distance to roads layer. And you may have to do some math because raw distance may not be directly the relationship. It may be that it's distance times 2, or it may be just as long as it's more than 200 yards from a road, we see them all the time, the particular thing we're looking at. But if they're less than 200, we hardly ever see them. It's more of a binary thing. In this case, what this is trying to say is that for whatever thing that we're concerned with here, actually, it's not very suitable at all if it's close to a road. The suitability increases, and then at a little over 1,000 meters, it starts decreasing again. So I don't know, like maybe a squirrel or some other thing that's kind of dependent on humans, or maybe this is just talking about houses. Okay, I want to build a new house. I don't want to be too close to an existing road, but I want to be close enough that it's not going to be crazy to build a road out to the existing road. So whatever you're thinking about, whatever area you're trying to determine is suitable for the particular topic, and there's so many topics out there, you need to basically come up with a mathematical way. I don't mean like hard. There's no calculus involved in here. I'm just talking about a mathematical way to determine the suitability. And then you need to know what GIS steps you would do to run these, because there's no button that says determine the suitability. That just doesn't exist in GIS. So you first figure out the roads layer. Then, once you figured out the distance to roads, you could say, okay, well, if the value is less than 500, turn it into a 0. If it's greater than 2,000, turn it into a 0. If it's any number in between here, feed it into this linear function. That's just a mathematical function. You have to figure out what that is, and you could put that in there. So here's a more concrete example. We've got elevation. We can use elevation to derive slope. We've done that in this class. Here's the mathematical relationship between suitability and slope. And then here is the slope suitability layer. So very rarely does any particular GIS layer just equate to suitability. You have to run processes to get to the suitability that you need. Combine the different layers by determining their weights. So I've noticed this a lot in my research, that there are different ways for determining the weights to combine various layers. One is oftentimes just start off unscaled. So once you have all of your suitability analysis, you can combine them by just either adding them up all together or just doing a simple overlay, depending on whether it's raster or vector data. You'll come up with an answer. It may not be the answer that you want, and so you might move on to just doing a common scale, because sometimes your suitability ranks in one data set will range from 0 to 100, and another they'll range from 5 to 10. And so the one that ranges from 0 to 100 could dominate. So you could simply come up with a common scale. You could rescale all your variables, all of your suitability maps, so that they have the same range. This is done a lot. You get a bunch of experts together in the field that look at the data and decide, well, this is twice as important as that, or this is really important, this isn't so important, so we're going to reduce the weight. This weight's going to be 0.2, this one's going to be 0.8. So you're basically saying that one's going to be this particular data set is going to comprise 80% of the results, and this other one's going to do 20%. Sometimes the way that gets started is to just rank order all of the input variables. Find the most important one. Then look at the result. Maybe I should have put this one above that. Then look at the result and start playing with the exact weights to make it look like you would expect it or want it to look. So this is just the math involved in doing a rank order determination of weights. So you decide parcel cost is the most important, parking density is the least important, and then second and third most important. In order to change a rank order into a numerator, you just basically reverse the numbers. This is very simple math, but you're just basically taking the 1 now becomes the lowest number, and 4 gets the lowest number gets the value of 1. And then you can weight everything using those numerator weights, divided by 10, and you get a number that will add up to 1. So if all your weights, if all your suitability scores are already on the same scale, going from 0 to 10 or 0 to 20, 0 to 100, if they're already on the same scale, if you multiplied them by these numbers and added them up, your overall result would then also be on the same scale. So here's another example of looking at what the general criteria are. Oftentimes, somebody will come to you as a GIS expert, or you'll be trying to solve a problem, and you'll have some general criteria. They'll say, okay, I'm looking for an area where the slopes aren't too steep. I want southern aspect. I'm looking for like a new place to put a building. Soils suitable for septic systems, far enough away from a road, to provide privacy but not too isolated. These are my general rules. Got to come up with areas that are suitable based on those general rules. Well, the first thing is to refine that criteria, to find out what they mean. What does it mean that what does it mean that slopes are not too steep? Well, we want it to be less than 30 degrees, because if it's greater than that, it's going to cost a lot of money to grade the landscape. Obviously, how many different categories does this produce? If we have slopes, let's say we have a bag of slopes. No, we don't have a bag of slopes. We have a landscape where where there's a bunch of slope values. Okay? A particular slope value is either going to be greater than or less than 30, right? Every single slope value, greater than or less than 30. Is that right? So there's two categories there. Everything can either be suitable or unsuitable. If I wanted to, I could take this general criteria and I could have come up with a refined criteria that didn't have a cutoff like that. It may have had 3 or 4 different categories. Okay? Slopes that are less than 10 are great. Slopes that are less than 20 are okay. Slopes that are less than 30 are acceptable. Slopes greater than 30 are unacceptable. Then I could have that, and then I could do the same thing with all of these. If I had 4 different categories for each of them, then I could use the rank order thing before, and I could come up with areas in my final product that were great, that were acceptable, that were okay, or that were totally unacceptable. You have to define both how you're going to refine the general criteria, and you have to define how you're going to combine those layers to determine what's acceptable. That's pretty much the point of what we're trying to get at here. Here's the diagram. It's more complex, but here's the actual diagram to create a suitable sites based on these criteria. We have our elevation layer. Our elevation layer gets transformed to both slope and aspect because those were both criteria that we wanted. And then we had to reclass both slope and aspect. In this case, we just have yes or no. Is it acceptable or not acceptable? And then we can do an overlay, probably an intersect overlay, because we have all the areas that are acceptable for slope and acceptable for aspect. And if we intersect those two, we'll get all the areas that are acceptable in both criteria. So then we have our terrain layer. Okay, so let's leave it there. The next one, this is just doing the raster to vector conversion, and you get suitable terrain. If I was doing this personally, I would put the raster to vector conversion before I even did the overlay. But there's more than one way to do things in GIS. All right, so we've got our soils. We reclassify to find the suitable soils. Our roads. We find the major roads, and we do some buffers and come up with those areas that are within a certain distance of the road, but not too far away from the road. That's what this was about. It has to be within 2 kilometers, but more than 300 meters. And then we combine all those in an overlay, and we get our suitable sites. So here's just this part in red, okay, and pictures to go with it. Slope, aspect. These are the areas that are acceptable. The black areas are the areas that are acceptable in slope. The black areas are acceptable in aspect. And so in order to see, I guess it's the gray areas that are acceptable in both. Okay, so in order to see which ones are totally acceptable, here's the suitable terrain. This mimics what you're going to do in the lab. We have a column that represents zeros means not suitable, ones represent suitable. Zeros represent suitable, ones means not suitable, ones represent suitable. So anytime if you multiply these 2 columns together, anytime you get a 1, it means that they're suitable. You get a 0, not suitable. That's very similar to today's lab. Soils, we could just do the reclassification. So that'd be a more simple, taking the soils, doing a reclassify, then doing a dissolve. Anybody remember what's the dissolve do? What does dissolve do? We talked about it like quick 1 week.
Doesn't it delete parts that are not, parts that are in the same bubble, I guess you could say?
Yeah, it removes the boundaries between two polygons that share a common value for a particular field. So after you do a reclass, it's often helpful to do a dissolve. Because imagine if you had, this would be a simple scenario, if you had population and you created a new column and you changed that population field into categories. Densely populated, not densely populated. Let's just say dense and not dense. If you did that, you would still have a bunch of polygons for every single census district. That, if you operate on tracts, you'd still have a bunch of tracts. You'd have neighboring tracts that both said they were highly populated. If you wanted to remove that boundary in between those two, that's what a dissolve does. In this case, we're dealing with the soils. So we're taking all of our soils and we're reclassifying them and saying the soil is either suitable or not suitable. Sorry, the other way around. Not suitable or suitable. So the zeros mean that it's not suitable. Ones mean that it's suitable. But we don't want to see all those lines anymore. We just want to see the suitable versus the not suitable. So after the reclass, we do a dissolve, and it removes all the boundaries, because it might have been that, I don't know all the different soil types, but this one was sandy, this one was kind of sandy, not sandy at all. That one was unsuitable, but the first two were both suitable. It may be that those polygons were right next to each other, and so when we did the dissolve, we removed the boundary between them. It makes it easier to do things like calculate the total area of all the suitable polygons when we remove the line between those two. Right? That's what a dissolve does. Here, in the overlay, all we're doing is saying we're taking the suitable terrain and the suitable soils and combining those two into a single soil. All right, next slide there. So now we're looking just at the roads. We do both a 300 meter buffer and a 200 meter buffer. So we've got two buffers, and we have to do an overlay between those two buffers. We could do in this case, I still think something like an erase buffer would be the best, because we're basically saying, okay, let's remove all of the stuff that's within 300 meters, but keep all the stuff that's within 2 kilometers. Anything that's beyond 2 kilometers, we don't want anyway. So if we did an erase overlay here, it would take out these little noodle areas that are close to close to the major roads. Remember, what did this first one do? What's the difference between this layer and this layer? The roads and the major roads layer. What's the difference there? The roads layer and the major roads layer. I mean, you could probably just describe the distance by looking at it. What's the difference between the roads layer and the major roads layer there?
The major roads is a lot less, road showing up, so it's the main track.
Right, okay, so how would you do that? It says extract on there, all right? How would you, knowing what you've done in some of the other labs, what could you do to take the roads layer and turn it into the major roads layer? So how would you take it off? I'm just asking you almost what. You can look at the fields, right? Okay? Look at this is raster data, it's vector data. So you look at the fields, and you might, what would be a way that you could find out what major roads? What if you had a field that said what the speed limit was? Okay? How could you determine what a major road is versus a minor road? What would be criteria? It doesn't have to be the criteria, but yeah, what did you say? Yeah, higher speed limits. So you might determine it's a major road if the speed limit is greater than 40 miles an hour. That might be your criteria. My point is, you have to come up with a criteria. So you have to find a column that you can determine a major road from, if that's what you want. Major roads. It may be that somebody's already done that for you. Okay? You're working with a city, and they already have a column that says major roads. In any case, you have to determine what that criteria is, and what would you actually do inside of ArcGIS to extract those. So let's say we bring up that column, and what's the tool called where I can bring it up and I say speed greater than 40, and I hit apply, and it makes all the little lines that are over 40, it makes them blue. What's that called? Yeah, select by attributes. Select by attributes is the way that you would do that. Once you have them selected, if I want to save them into a new shapefile, what's the way I do that? So that I only have the major roads. Yes, go to export data, right? There's another way to do it. One's not better than the other. You could go into our toolbox, and there's just a tool called select. And what it does is it does those two steps in one step for you. But that's the way you've done it in the labs. What she described is perfect. That's exactly what's been done in the labs. So you would have to do that in order to get this layer. Then you run buffer tool. You've done that in the lab. You run the buffer. You run it again. You run the other buffer. Then you do an erase or a union, and then you could do another select by. If it's whatever column represents this layer, you could say if it's in that column and not in this column, then export, then select it, and then export it again, and you have this. And finally, this is just showing that you're clipping it to the study area, just for whatever reason. I don't care about what's outside of that study area. All right, and then finally, you're just combining them all through an overlay. You do an overlay, you do a reclass, and then at the end, you might want to do another dissolve. Anything where all four columns are the same, go ahead and dissolve it for me. And you could combine them. You could make the end result. If you say it has to meet every single criteria, you could just say, okay, well, it has to be one in every column. Or you could make a new column and add these up. You could say the areas with 4 matched every criteria. The areas with 3 matched 3 of the 4 criteria, and so on. I had another project. This one I'm really not sure if it's running. Let's see, because it was down for a little while earlier. Another project that did exactly this. So this one had a bunch of different criteria under condition, threat, sensitivity, and exposure. Looks like it's down. Oh, no, it's popping up. Move this map over. And each of those different criteria, the way that they match up, they wanted to know if it matches the exposure and the sensitivity and the threat and the condition variables. In other words, if they are all met, then what we want to do is call that lower risk. In other words, if these are all good, that's lower risk. If exposure is the highest, if exposure is risky, but these other ones aren't, then it's a different category. In other words, they wanted to come up with every single possibility. Okay, if this one's good, this one's good, this one's good, this one's not good, that's another one. If this one's good, that's not good, and that's not good, that's another category. They had a bunch. So you have to come up with a mathematical way to do that. So let's go back to our example here on this slide. Okay, the mathematical way to do that would be to combine these numbers as if they were all multiples of 10. So in this case, that would be 0. This would be 100. This would be 10. 100, 10. This would be 110. So you come up with a bunch of different possible values. And that's exactly what's going on in the background on this website. The only values you're going to get are either ones or zeros. But you have 1, so all the possible values are 0, 1, 10, 11, 100, 101, 111. So there's like, I don't know, 32 or so different, maybe 64 different possible values in this legend. Okay? So you just have to think of a way to combine it mathematically to produce a unique value for every unique value that you want. In this case, we're just going to say it's either suitable or not suitable. In other words, they all need to be equal to 1. So we could just do another select. Select road suitability is equal to 1, soil suitability is equal to 1, terrain suitability is equal to 1, and final suitability is equal to 1, and we get our result. Your final lab is going to be similar to that today. Your lab today is going to be similar to that, where if they meet all the criteria, different criteria, but if they meet all the criteria, then those are the areas that you want to consider. All right. Got a little extra bullet point there. So these are the things that you need to remember when you go to do cartographic modeling and GIS. You need to make sure that the problem is clearly specified. You're often going to have to times go back to either your own brain if it's an independent project you're doing, or if somebody's directing you on this project, you're going to have to go back to them and say, okay, I need that criteria more clearly specified in order to solve the problem. Obviously, it needs to have a spatial component, or it's not really appropriate for GIS. You could do it in some other problem. I mean, you have to have a bunch of maps, a bunch of map data in order for this to work. You need to determine the spatial and attribute accuracy that are required for the analysis. So something that we talked about in today's lecture, it's something that we'll talk about before we do the test review next week. But it should be kind of obvious that, let's say I want to do, we'll move today's ruffed grouse, which is a bird, habitat down here to Mississippi. Let's say I want to find appropriate gopher tortoise habitat. Well, if I know that gopher tortoises live in piney woods areas, they like the tall pine trees that we have here, right? But if I have like a map that was created that shows all of the different land cover types in the whole United States, and it's pretty coarse, and it just has one polygon, it's kind of drawn around the southern, the south half of Alabama and Florida and Mississippi, then my answer is going to be that area. If that's what I'm looking for, it's okay. But if I'm doing this just for South Mississippi, I want to have a very detailed map that shows me exactly where those types of forests exist. Because they don't exist everywhere. Like in the river bottoms, like close to rivers, we get trees and hardwoods and things like that. Those areas may not be as good as the upland, basically the old sand dunes and things like that. So what I'm trying to get at here is you need to have the data to drive the answer that you want to get. So if you have general data, you get a general answer. If you have specific, high grain, very precise data, you're going to be able to more precisely answer your question. Okay? So does the spatial and attribute accuracy and precision required for the analysis exist? And if not, you have to get it. The minimum mapping unit has to do with the scale. That's what MMU means, minimum mapping unit. Sorry, I should have said that earlier. Also, when you're doing all this overlay, like in this diagram, it's really important that all of your data overlays. So one of the things that you have to do before you even embark on this project, you collect all your data, and then the next step you need to do is make sure that all your data lines up. So you bring it all up into ArcGIS. Because sometimes, it almost always happens, some students will email me and say, hey, I got these two data sets. I'm going to bring them up in ArcGIS. One, I can only see one at a time. The other one's like off, way off somewhere. Well, it's because your data is in a different coordinate system. So make sure that all your data is in the same coordinate system. Sometimes you might have to run the tools to change the projection or define the projection. It's actually more often that you have to define the projection than change the projection. All right, you need to know the extent of each layer. Obviously, your data has to overlap, has to be in the same area. Okay? If you're trying to do analysis in South Mississippi, you need to have these layers for South Mississippi. The layers that are included in your analysis. Where do you look for data? If the extents are different, think about how this will affect the analysis. You might have to do some just house cleaning, clipping off the extra data if you have more data than you need. Because it takes a few minutes to run each of these GIS processes. If your data is actually really high resolution, really precise data, it could take 10, 15 minutes. Some of the data that we collected from the boat drones, basically this boat that's just going back and forth over the water, it's collecting 4 pictures every half second. So it creates like 10,000 pictures in a matter of an hour. And so in order to run that process, it takes a really, really long time to combine all those images. But anyway, when you operate with GIS data, you're going to encounter something like that, and it's always helpful if you can clip off the stuff you don't need, because it'll decrease the processing time later in the cartographic modeling process. All right. If you're going to, if your data sets, and it's just fine if they do. If you have some raster data and some vector data, that's okay. Because sometimes that's what you need to answer a specific question. Almost all elevation data is in raster. So if you have a question that involves elevation in your question, some sort of criteria about elevation, that's going to be a raster data set. If it involves roads, it's almost always vector data initially. And so you have to decide what your final result is going to be. It's going to be, your final result is going to be kind of a continuous layer of from totally unsuitable all the way up to suitable, but different gradations. It might be best if your answer was in a raster data set. If you picture your final result to be ones and zeros, or maybe just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it might be best if your final answer was a vector data, because it's better at storing discrete numbers. Okay? And so you have to think about what you want your final result to be in, and then think about how you're going to combine the vector and the raster data, how it's going to come into the process. If we go back here, this layer started off raster. It changes, I said I do it somewhere in here. But just as part of the process that's going on, there's a raster to vector conversion where you'll get a suitability vector data. In other words, you get polygons of what areas are suitable at some point. And those polygons get combined with these these other data sets, which are polygons. We didn't have to do it that way. We could have taken the soils layer and converted it to raster so that we had a different raster overlay, and we just added all the data sets up. That's what's going on in that first example that I showed you with the oysters. In the background, it's just adding them all up. All right, so you got to convert. When you do convert, you have to think about, if you convert from vector to raster, you have to think about how big your cell sizes are going to be, because it'll really make a difference on how much data you'll get. If you're going from raster to vector, one of the biggest questions is, how precise am I going to be? Like, if I have a bunch of cells, am I going to follow all the cell boundaries, or am I just going to follow like the center of each cell around? That all gets into how precise you want to be with the result. Okay, that's the end on there. Why don't we take a 15-minute break? Come back at 2:30, and I'll introduce the lab and talk about what you need to do. I'm going to talk about both of the labs because there's a lab that's technically for today, but then there's also the final project lab, basically, and how you would